All right, we're back. More computer vision. So for logistics stuff, homework 3 is out right now. You guys are working on it. Optical flow, it's due tonight. There are some random issues with OpenCV. This is the same logistics slide from last time. I'm not going to do the demo again. How are people feeling? Are there any like big issues or anything going on? Anyone have anything they want to talk about? Yeah.
How close?
Not. I mean, pretty close. Yeah, the general algorithm should be right. We don't have any tests for this, so I think Connor is just going to go through and look at because there's just a few little places where you're doing anything, so it should be pretty straightforward. It was meant to be like pretty easy. Any other random questions or anything? Cool. All right, let's talk about what we talked about last time. So we were talking about sort of logistic regression, and then we were generalizing this to the case with more classes, basically. So we were talking about Softmax regression, which is basically just this normalized exponential function where the input is going to be some vector, and the output is just going to be some scaled version of that vector so that we get back a probability distribution. And how this actually works is we're going to take all of the, there we go. We're going to take all of the elements of the vector and calculate e to the power of that element. And then we're going to divide all of those elements by the sum of basically the result of this calculation for all of the elements in the vector. So for example, if we're taking, say that we have some model that we run, and the sort of unnormalized output from this model that we get is just this vector 1, 2, 7, 3, 2. What Softmax is going to do is basically calculate e to the x, which is these results here, 2 point something, 7 point something, 1,096 point something, etc. We're going to calculate basically then the sum of this vector, which ends up being about 1,100, and then we're going to normalize with e to the x divided by the sum of e to the x, which ends up being sort of this probability distribution here. And the nice thing about this is that this probability distribution is going to sum to 1, and all of the elements are going to be between 0 and 1. So it actually is sort of a well-behaved probability. Now, what you can sort of think of Softmax as doing as literally what the name is, it's a soft version of the max function. So another way to create a probability distribution out of this vector would just be pick whatever the largest element is, set the output for that element to be 1, and set the output for all of the other elements to be 0. In that case, we'd get 0, 0, 1, 0, 0. Instead of doing that, Softmax is this smoothed version where we don't necessarily just pick the largest element, but we're going to throw a lot of the probability distribution behind the largest element instead of some of these smaller elements. So then we talked about basically using Softmax to do this multi-class prediction task, multinomial logistic regression, where the probability that a data point belongs to a particular class, we're just going to multiply the weights for that class by the input vector. We're probably going to add on some bias, and then we're going to be left with a vector, and we're going to run the Softmax function on that vector, and that's going to give us sort of a multi-class predictions. And we talked about how this is pretty easily represented as basically some matrix operations where we have our weight matrix here, and we can think of this weight matrix, the top row is basically the weights for class 1, the middle row is the weights for class 2, and the bottom row is the weights for class 3. So when we multiply these matrices by our input and add on our bias, the probability for class 1 is going to be proportional to the weights for class 1 multiplied by the input. The probability for class 2 is going to be proportional to the weights for class 2 multiplied by the input. But we're running this Softmax on top, so we get this nice probability distribution as a result. And we talked about basically one possible application of this is on this data set MNIST, which is a really common image classification data set. It's sort of like if you have a new idea for how to perform some image classification algorithm or some new algorithmic thing that you think might work, sort of the first thing you do is test it on MNIST to see if it has sort of any shot of working. Because it's like a pretty small data set, and it's pretty easy to kind of get a handle on. So it's just 50,000 images. They're small grayscale images, and they're the numbers 0 through 9. So one thing that we can do with this is just train sort of a simple linear classifier that uses softmax regression. The input is just going to be sort of all of the pixel values, and what we're going to do is just put all of the pixels into one vector. So we don't actually keep around any notion of the structure that we had in the image before. We just have one long vector with all of the pixel values. We can train this softmax regression with stochastic gradient descent, and we get pretty good accuracy on this data set, 95%. With neural networks, we get much higher than this, but it's still pretty cool. We talked about support vector machines, where what we want to do is just back to this for a second. A little preview over here. We talked about support vector machines, which are another version of this linear classifier that we've been discussing, but we want to find some notion of what the best classifier is, because if we're trying to, for example, classify between these two different points, there are a bunch of linear decision boundaries that will correctly classify all of those points. And so what we want is maybe some notion of what the best classifier is, sort of what the classifier that separates these points the most is. And one thing we could think about is basically maximizing the margin between this, between our decision boundary and sort of the closest points on either side. So in that case, it would be this black point and these two white points. And what this is doing is finding sort of this maximum margin classifier, and these are called the support vectors for this support vector machine, because they're sort of the points in the data that actually matter when we're trying to figure out what the correct linear classifier is. And in practice, instead of finding sort of the classifier that has the largest margin, what we're going to do is set the margin to be equal to 1. So we're going to say that the distance between this line and these points is going to be 1, and then we want to minimize these weights such that the margin between the points and our decision boundary is at least 1 for all of the points. And the reason that we're doing this sort of different version where we're setting the margin to be 1 and minimizing the weights is because if we just think about maximizing the distance between this sort of line and these points, the way that we're calculating this distance is just this dot product of the weights and the features of our input. And so if we have any sort of linear classifier that correctly classifies all of these points, one way to maximize the margin would just be to make the weights really, really big. And for any correct linear classifier, you could just scale those weights to be larger and larger, and you would get sort of an infinitely large margin. So it doesn't really work if we actually think about maximizing the margin with unconstrained weights. So what we're going to do is just constrain the margin and then minimize the weights. It's sort of just kind of the flipped version of this problem. And support vector machines are used all over the place in sort of old school computer vision. So one example is person detection, Dalal and Triggs, where we're going to train an SVM on hog features, and then we're going to scan over the image and run our classifier a bunch of times and decide, is this a person or is this not a person? And in particular, we're going to run at a bunch of different scales and sort of every location in the image. And this is sort of a classic sliding window object detector. And it involves just running this classifier, tens of thousands or hundreds of thousands of times per image. But it's OK because we're using this pretty simple linear classifier, this SVM, where we're just doing this dot product. So it should be pretty fast to actually do this in practice. We also talked about a more advanced version of this, deformable parts models, which kind of generalizes this detection problem a little bit. So instead of just learning a single filter that is going to detect the class that you're interested in, we're going to learn sort of a base filter, which will be, generally the object looks sort of like this. We're also going to learn these parts filters, which are going to say, generally this object has these components, maybe like a head and some arms and some legs. And we're also going to learn sort of location information about where those parts typically fall. So the head is normally somewhere near the top of this object. The arms are kind of near the side, and they fall within some range. And the feet fall within some range as well. And then we can run sort of our base model over the image. We can also run these part filters over the image. And using the probability distributions that we've learned about where these parts are, we can basically combine all of this information together and get some end prediction that factors in both, what does the object typically look like, but also are there parts of the object that sort of have high responses nearby? Are they within some window that we would normally sort of expect these parts to be in? And if we use this deformable parts model, we can get a much more accurate detector than just with sort of this single filter that we were using before. And actually, in practice, deformable parts models use multiple filters per object to correspond to different viewpoints. So for example, if you think about a bicycle or a car, these things have sort of a very sort of canonical look if you're looking at them from the side, but they also look much different if you look at sort of them from the front or from the back. So what deformable parts models does is it trains 4 or 5 different detectors, different models with both a base filter and parts filters for different viewpoints of the object. And then at test time, it sort of can recognize objects at multiple different viewpoints, from the front, from the side, from on top, et cetera, because it will run basically all of those filters over the image. And deformable parts models are interesting because they're learning some extra information that we don't actually explicitly give the model. So all we're going to give the model is basically bounding boxes of this is the object, and the object doesn't appear anywhere else in this image. But it's actually able to learn all of this extra information that corresponds to what these parts are, what they look like, and where they generally fall in the object. We're not going to go too much into this, but this is an example of adding in some sort of additional information to this SVM and learning what's called a latent SVM. So we can think of basically, in computer science, for some reason, they use this word latent. This is just information that you don't know, or sort of hidden information. So objects have parts, and those parts generally fall in certain areas, but we don't necessarily know that beforehand. But we can learn this latent SVM that learns what the parts look like and what the locations of those parts generally are for these different object classes. Another thing deformable parts models uses that's interesting is this notion of hard negative mining. Because if you think about images and you think about sliding window detection, where we're going to look at like sort of every single little patch in an image, there are going to be a lot of negatives. There are going to be a lot of places where there aren't a bicycle, for example. And there are only going to be like a few bicycles maybe in one image, and you're going to have a lot of images that don't have any bicycles. So you're going to have a bunch of negative examples for every class and very few positive examples. So we're just going to rebalance training so that we have sort of an even number of negative and positive examples. And in particular, the negative examples that we want are sort of the ones that are already hard for the current detector. So we're just going to take misclassified examples in our training set and train on those as negatives and the ground truth as the positives. We also talked a little bit about image classification, which is just even sort of simpler problem than detection. Given an image, we just want to know like what's in the image. We can kind of assume that there's basically one thing in the image. It's just an image of a person or an image of a dog or an image of a chair. And sort of the old state of the art for doing this is we're going to extract a bunch of features and then train some linear SVM. And there's this popular data set called ImageNet that we'll talk about at some point in the future that has basically 1,000 different classes and about 1 million images. And when we train this sort of basic model, we get about 54% accuracy, which is kind of cool. But the problem with sort of all of these approaches is that they're really sensitive to basically what features you pick to feed into your machine learning model. So machine learning is all about these features. And if we have really good features, we're going to be able to learn a really good model. And if we don't, we're not going to be able to learn the model that we want. So instead of basically having humans choose what all of these features that we're going to feed into the model are, hog features or SIFT features, whatever, instead, we can think about neural networks as letting the machine learning algorithm decide what features are important for a particular task. And neural networks have been super influential and sort of pushed the state of the art really far in computer vision. We've made some really big strides. And this is just talking about feature engineering is this core problem of like, if you have really good features, it's really easy to separate out the different classes from each other, or sort of predict the function that you want to model. And if you don't have these features, it's much more difficult. And for example, a linear model can't do this feature engineering for you. Sort of a human has to come along and say, oh, I think these are the right features for this problem. And so what our neural network is going to be is just some series of layers that is going to do linear combinations of the previous layer. And we can think of this as sort of performing feature extraction. And then at the end of this, we're going to have some sort of linear model that is either a linear classifier or a regressor. And it's going to perform sort of this combination of feature extraction and the final prediction task that we care about. So this example just has a single layer, but we can think about basically stacking these feature extraction layers on top of each other kind of indefinitely. People use models with a lot of layers. And one important thing is basically we have this function phi that we're going to apply after we do this linear combination at every layer. And phi is called our activation function. And what we choose for phi is sort of really important. If we basically just use a linear function here, then we can kind of collapse this entire model into just one linear layer, sort of one. Our output is just going to be one linear combination of our input. And that's not very interesting. We've already discussed that linear models have this problem where they can't do kind of this feature engineering on their own. So what we're going to actually pick for phi is something nonlinear. And in particular, we have this cool theorem. That's the universal approximation theorem. So this basically says if we put some constraints on what phi is, if it's non-constant, bounded, and monotonically increasing, then we can correctly model any function within some constraints. And those constraints are basically that function is itself has a bounded domain and a bounded range. And this is really cool. So we went from basically when phi was linear, neural networks were just linear models, to if phi has just a few constraints placed on it, it's sort of something a little more interesting than linear. We have this sort of infinitely powerful model in some sense. Or we have this thing that can model any continuous function. So it's a very powerful machine learning model to use. But in particular, sort of the universal approximation just says that it's possible to come up with weights and some hidden layer that will correctly model this function. It doesn't tell you how to do it. So we have to sort of learn for ourselves what the correct weights are and what the correct configuration of this neural network is. So in general, we're going to use gradient descent when we're optimizing something like a neural network. And so first we sort of went over what gradient descent looks like when we're just learning logistic regression. And all we're really going to do is at every time step, for every weight, we just want to calculate the gradient, sort of the partial derivative with respect to that weight of our loss function. So with logistic regression, we talked about we're not going to use loss, we're going to use log likelihood. But we have the same sort of concept where basically what we're interested in is calculating the partial derivative with respect to all of these weights. And then we're just going to add on some scaled value of that partial derivative to that weight. And we discussed before, basically, we have this loss function that describes sort of how well or how poorly our model is doing. And what gradient descent is doing is just kind of pushing the weights in one direction or another to minimize or maximize the function that we're interested in. So if we're talking about a loss function, we're going to basically calculate which direction the loss function increases the most, and then we're going to push the weights in the other direction with the hope that in that direction the function is going to decrease the most. So we're basically, we can't find some closed form solution for these problems. We can't just say like, okay, let's calculate directly what the weights are that minimize this loss function. But we can calculate this sort of very local information using gradients. Gradients will tell us basically what the local structure of this function looks like. And then we can make these really small changes to our weights, which over time will decrease our loss function further and further until we get to hopefully some minima. And so we just went through a basic kind of simple example where if we have logistic regression or some just linear model here, and in particular our input is just going to be these two numbers, 10 and 1, and our output p is going to be some linear combination of those two numbers. And imagine that we want to make p larger. So y, which is the sort of correct value for this data point, maybe is larger than what our output p was. And so we want to figure out basically how to modify these two values. Well, it's clear that if you want p to be larger, and we have these two numbers, they're both positive, and our output p is just some linear combination of them. So we want to increase the weights along both of these edges. And in particular, what ends up happening is our partial derivative is based on the input. So the partial derivative is our gradient y minus p times x1 for weight 1, and x1 is 10. So we're going to modify this weight 10 times more than we're going to modify this weight. And that actually makes a lot of sense when you kind of think about it intuitively. We're thinking about the gradient, which is the direction of most change. If you think about making equivalent changes to these two weights, the change that would matter a lot more is the change that you make to weight 1, because it has this much larger value that you're inputting for x1 than you have for x2. So changes to weight 1 matter a lot more than changes to weight 2, and so the gradient is larger for weight 1, so we're going to sort of push weight 1 a little bit more than we're pushing weight 2. But both of them we're going to try to make larger in sort of this example of like one step of stochastic gradient descent. We also talked about basically, imagine that we feed in this other data point, -1 and 1, and we have the same situation where y minus p is positive. We want p to be larger. How are we going to modify the weights now? Well, now we still have the same formulation. Our partial derivative is the input times this gradient y minus p. And for this weight, weight 1, that's going to be negative because our input is negative. And that sort of makes sense. We don't want to increase the amount that the negative number sort of matters. So we're going to decrease the weight. And in particular, if the weight is already negative, then decreasing it more makes it more negative, which makes this multiplication more positive, which will make p larger. And W2 is going to be basically the same calculation where you're multiplying x2 times y minus p. So we're going to increase weight 2 and we're going to decrease weight 1. And since they're both 1, we're going to use sort of the same factor, but just a different sign for both of those numbers. So does this kind of formulation for logistic regression make sense to people? Do people kind of understand gradient descent and why this is meant to just be kind of like an intuitive example, right? Like we know that we want to make p larger, so we push the weights this way. If we wanted to make p smaller, we would push the weights in the other direction. Do people sort of understand what's going on with gradient descent in just this simple linear model? Seems like we have some nods. Cool. Now we're going to talk about neural networks, which are a little bit more complicated. So imagine that we have this neural network, and we're just going to use linear activations for right now. How do we predict our output p? So we have some weights for w, 3, -2, -1, 4, 5, 3. We have some weights for v, 2, 5, and 1, -1. And we have some input to this model, 2 and -1. Well, first we're basically going to calculate the hidden layer neurons, which we're just doing this weighted sum. So 3 times 2 plus -1 times -2, et cetera. It's pretty easy to see basically why our output is going to be 8, -6, and 7 for this hidden layer. And then we're going to take our hidden layer and propagate the information forward one more time, where we're just going to multiply the input, sort of the hidden layer neurons, by the weights that come out of our hidden layer and connect to p. And again, we have 8 times 2 plus -6 times 5 plus 7 times -1. And we have some output for p. Now imagine that we want to start making some changes to this network to predict some different value. So for this data point, 2 and -1, imagine that p was supposed to be like 50 or something. So what we want to do is modify the weights of the network to increase the final prediction P. And what we can think about is doing this same process. So at sort of the final layer, at sort of our last prediction layer, remember that this is basically just our linear model on top of our feature extractor. And we just went over in logistic regression how we're going to make changes to the weights to make the corresponding change that we want to our output. We're going to do basically the exact same thing here. So if we want to make P larger by some amount, we're going to look at the input and multiply the input by sort of the amount that we want to change P. And so for this example, we have this arrow that's sort of strongly up, and we see that this is a positive number, so we're also going to want to increase this weight. Whereas for this middle connection, we have a -6, and we want to make the input larger. So we're actually going to decrease the weight that sort of corresponds to this connection. The weight before was 5, and we probably want to shrink that down to something smaller so that this -6 contributes less to our final prediction. And we also see that we have some large positive number here, and we want to make our final output larger, so we just multiply the amount that we want to make this larger by this input, which is sort of strongly positive. So we'll be increasing basically the top and bottom weights and decreasing the middle weight. And now the question is basically, what are we going to do with this sort of intermediate layer, or sort of how are we going to modify these weights? Well, we know basically how to modify weights if we have some sense of error for a node. We know how to basically modify the weights that are coming into a node if we know the error associated with that node. All we have to do is basically look at the connections from the previous layer. So one thing that we could think about doing is basically figuring out what the error is at this layer as well. And if we had some notion of basically what the error is at this layer, it would be really easy to calculate what our gradient steps should be for the weights that connect to that layer. And that's what backpropagation is going to do. So for example, we have this middle unit, which is sort of this strongly negative unit. And we have this positive weight, 5. And so we know that this middle connection here is contributing a lot of negative information to this final output. And we want the final output to be more positive. So what we can do is just take this information here, which is saying that we want to increase the final output P, and we can multiply it by this weight, 5. And from that microphone's off. And from that multiplication, we can see that basically we want to increase the value of P, and we have this positive connection. So we should increase the value of this intermediate node in the hidden layer. And we can talk about doing this for other values as well. If we look at sort of the top and bottom, we have a strong positive neuron here, and it's going through this positive weight, and we want to make the eventual value more positive. So we want to make P larger, but this weight that's connecting it is pretty small. So our gradient information is basically going to multiply the amount that we want to increase P by this weight, and we want to basically shift this node to be larger. But since this weight is pretty small, the sort of error associated with this node is correspondingly going to be sort of small. And we have the same kind of situation down here, but just with a flipped sign. We want to increase the value of P, and the contribution from this node is basically going to be the opposite sign. It's going to be -1 times whatever was in this node. So we're going to take our gradient information at our output, multiply it by our weight, -1, and we sort of get this flipped sign, but sort of a small contribution from this node. So now we have some form of basically error at our hidden layer. We know that basically the error associated with this node, we want to basically increase the output from this node. We would like to increase the output from this node a lot, and we would like to decrease by a little bit the output from the node at the bottom. And now we just have the same sort of problem that we had before, where we have some error information and we want to figure out how to update our weights. Well, we can do the same computation that we did before, where we're going to take the input values and multiply them by the error, and that's going to be the amount that we modify each of these weights. So this is sort of an intuitive overview of the backpropagation algorithm, and all we're doing is basically calculating partial derivatives for each of the weights by backpropagating our error through this network. And so what we're going to do as sort of our learning algorithm for doing stochastic gradient descent with neural networks is we're going to forward propagate the information from the beginning of the network. We're going to calculate our error at the end of the network. And then we're going to backpropagate that error through the entire network and calculate the weight updates as a way of calculating sort of these partial derivatives for each of these weights in the neural network. So this was with linear activations, but the process is going to be very similar when we actually have some activation function phi. And in particular, all we'll have to do is sort of calculate the gradient of phi with respect to the input x for each of the neurons as well. And we'll see how this plays out as we start actually getting into the math. So imagine that now we basically have this neural network, and we're going to start using these activation functions. So our final prediction, basically, f of x, is going to be the forward propagated result through this neural network. So we have this hidden unit, or sort of this hidden layer, where the output is this matrix multiplication of the input x times the weights w, and we're going to apply this function phi to that output. So for example, h1 is going to be phi of w1x1 plus w2x2. And we have our output p. We're just going to use sort of a linear activation on the output. So p is just going to be the hidden layer h matrix multiplied by the weights v. And so it's just going to be this sum, v1h1 plus v2h2 plus v3h3. Now, imagine that we're using this linear sort of output, this neural network, to do a regression task. And in regression, commonly, a loss function that we might use is L2 norm, or a lot of times people use 1/2 L2 norm to make the derivatives just a little bit easier. You don't have sort of an extra 2 floating around. So what we're going to want to do is basically, at all of our weights, calculate partial derivatives with respect to our loss function. So first, let's just imagine calculating this partial derivative with respect to one of the weights, say v2. So v2 is a weight in sort of this last layer. And we've already seen this basically with logistic regression. What we're going to end up with is, if we look at this, we have a different loss function, but the partial derivative information sort of ends up being the same. We take this square down and multiply it by 1/2, and it goes away. And then we take the gradient of kind of the inside of this loss function. So we end up with y minus this term here, which is just f of x, kind of the prediction of our model, times the negative partial derivative of v2 with respect to the prediction of our model. And when we actually expand out what this prediction actually is, it's just phi applied to, or sort of what this prediction is, we can see up here is this term is sort of h1 phi applied to x1 w1 plus x2 w2. And so we're going to do h1 times v1. This term is h2. We're going to do h2 times v2. And this term is h3. We're going to do h3 times v3. And so if we think about basically taking the partial derivative of this whole term with respect to v2, the only term in here that actually matters is sort of this middle one. So we can kind of just get rid of these other ones because they don't have any term for v2 in them. And then when we take the partial derivative of just this middle term with respect to v2, we just get rid of v2, and we're left with our output from h1, or sort of our output from h2, sorry, which is phi of x1 w3 plus x2 w4. And so our weight update basically is just going to be this term. And this term corresponds to sort of the difference from the expected output y and what our model's actual output was, multiplied by basically the information coming from H2. And this makes a lot of sense with what we were talking about for logistic regression earlier. Remember that, and so again, all we're going to do is basically substitute in H2 here for that term and move the negative sign to the front. And remember that we are doing gradient descent when we're talking about loss functions. So our weight update rule, we're just going to add on some scaled version of this partial derivative of the loss function with respect to the weight that we care about, v2. So the weight v2 is going, for some future time step, is just going to be the current weight plus some scaled version of this partial derivative. Now imagine that instead of doing this weight v2, we want to think about the partial derivative further back in the chain. So maybe the partial derivative for w2, which is the weight right here that connects x2 to h1. Now we're going to go through sort of the same process where we are taking the partial derivative of our loss function with respect to w2. Again, we just take the 2 down, it cancels out, and then we have to take the partial derivative of the inside of this as well. The partial derivative, so y is just some constant, so it goes away, and we're just talking about the partial derivative of the output of our model with respect to w2. And now we sort of have to actually care about the inside of this function instead of last time where we could just kind of ignore it because all we were looking at was v2. This time we care about w2. And so when we're thinking about the partial derivative of w2 with respect to our output, this is the output of our model. We have these two terms that correspond to h2 times v2 and h3 times v3. They don't have any information that comes from w2, so they're just going to go away when we do this derivative calculation. So we can kind of forget about them and just focus on this term here that has information with respect to w2. And what we're going to do is basically pull out this scalar value, v1. And a lot of these operations are basically taking advantage of this chain rule that you guys probably remember from calculus, where the derivative of f applied to g applied to x is the derivative of f applied to g of x times the derivative of g of x. So we want to take the derivative of phi applied to some value. We are just going to take the derivative of we're just going to calculate the gradient of phi applied to that value and multiply that by the partial derivative of what was sort of what the function was being applied to. And when we look at the derivative of sort of this term, this is just a weighted sum, we're looking at w2, so the only thing that matters is x2. And we end up with this final sort of extensive term. What is kind of going on here? We have our initial sort of error that we had at the output p, and that error is just the expected output that we sort of wanted from this training example minus what our model actually gave. So this is sort of our model at our output p. And then we kind of want to backpropagate this information to our node h1. And the way that we're going to do that is through this node v1. So we're going to backpropagate this loss through v. But then we also have to basically do this gradient calculation here because our output h1 is phi applied to some sum. So we can sort of think of this entire term that's circled in purple as being the model error associated with kind of the input at h1. And then all we're going to do is, we have some model error associated with this node, and we can just multiply that error by the input to the weight that we're interested in this case it's x2, and we'll figure out the partial derivative with respect to w2, which is the thing that we actually care about. Another way of thinking about this is calculating a bunch of partial derivatives at various locations in the image. So very quickly, just kind of to yourselves, think about all of these partial derivatives. So for example, this partial derivative is going to be the derivative of this weighted sum w1x1 plus w2x2 with respect to the weight w2. We're also going to think about this partial derivative, which is the derivative of this term h1 with respect to this weighted sum w1x1 plus w2x2. And remember that h1 is just phi applied to w1x1 plus w2x2, and et cetera. Think about the partial derivatives of p with respect to h1, the partial derivative of p with respect to v1, and the partial derivative of our loss with respect to p. Think about it. Write some of them out. I'm going to go get a drink. All right, who's got some answers for me? What is this partial derivative? Someone said it? Yeah. Okay. What is this one? Something weird happened there. Someone said 0. About that. So the h1 here is phi applied to this weighted sum, right? So we want to, in essence, we're taking the derivative of f of x in with respect to x. Does that help anyone? Just some function. It doesn't matter what it is. I didn't fill this one out for some reason. I'll have the answer to that one in a second. So what is the partial derivative of p with respect to h1? It's just, the derivative of p with respect to h1 is just v1. Sort of it's the only term that matters with respect to h1. And the derivative of this weight vector v1 with respect to, so the derivative of p with respect to this weight vector v1 is correspondingly going to be h1. Again, we're going to take the partial derivative of p, but this time with respect to v1. And so the only sort of information here that corresponds to v1 is this term h1. And finally, the derivative of our loss with respect to p is this function that we already talked about, where basically we're doing the L2 norm, and the L2 norm is just y minus f of x squared. And we're going to talk about, instead of doing y minus f of x squared, we're going to do 1/2 y minus f of x squared, which makes the derivative just a little bit easier. So remember that p is just phi of x times w times v. So that ends up being sort of the partial derivative there. I don't know what happened to, oh, it got like shifted down. That's what's going on here. Okay, you can sort of see it, I guess. I'll fix my slides. But all it actually is phi prime. So the derivative of h1 with respect to w1x1 plus w2x2 is just going to be phi prime of x1 w1 plus x2 w2. So the derivative of f of x with respect to x is just f prime of x. And that's all we're saying here. We don't know what phi is, so we don't know what phi prime is. But once we sort of pick a phi, we'll be able to figure out what phi prime is. So how do we update this weight v1 if we're doing stochastic gradient descent? Well, the information that we want is the partial derivative of the loss with respect to v1. And we can think of this as basically being the partial derivative of the loss with respect to p multiplied by the partial derivative of p with respect to v1. if we think about sort of this multiplication, the terms dp in the numerator here and dp in the denominator here are going to cancel out, and we'll be left with just dl dv1, which is sort of the term that we want to calculate. And we already know these two terms, so dp dv1 is just going to be h1, and dl dp is going to be y minus our output, phi of xw times v. So we have our update rule, or sort of our partial derivative for v1. Correspondingly, imagine that we want to figure out our partial derivative of our loss function with respect to w2. How would we update w2 in this scenario? We have sort of the same kind of long multiplication where all of these terms are going to cancel out with each other. So we have dl dp and dp dh1. The dp's are going to cancel. We have dp dh1 and dh1 d sum, and the h1s are going to cancel. We have the dh1 d sum and d sum dw2. The d sums are going to cancel, and at the end we'll be left with just the derivative of the loss with respect to w2. And we know each of these individual components as well because we just calculated them. So the partial derivative of the weighted sum with respect to w2 is just x2. The partial derivative of h1 with respect to this weighted sum is going to be phi prime of that weighted sum. So remember that h1 is just phi applied to the weighted sum. So the partial derivative of f of x with respect to x is just going to be f prime of x. We know what dp dh1 is because we just calculated it. It's v1. And we know what the partial derivative of the loss with respect to p is going to be. It's just the difference of the output that we wanted to get minus what our model actually predicted, phi of xw times v. One more way of thinking about backpropagation. So we have our loss that we calculated at our output, which is the partial derivative of the loss with respect to the output p. And we want to calculate the partial derivative of the loss with respect to v1. So all we're going to do is multiply h1 by this loss at p. And then we're going to backpropagate our loss information to h1. And how we're going to do that is just multiply the loss with respect to p by this term v1, and we'll get the loss with respect to, or the derivative of the loss with respect to h1. And then we sort of have to take into account this activation function phi. So we're going to multiply the derivative of the loss with respect to h1 by phi prime of our weighted sum to get the derivative of the loss with respect to the weighted sum. And then when we want to calculate basically our partial derivative with respect to w2, we can just multiply the derivative of the loss with respect to this weighted sum by this term x2, and we get the derivative of the loss with respect to w2. So that's all that backpropagation is. We have sort of these two basic things that we're doing where we have some loss associated with some node, and we multiply it by the input to a particular weight to calculate the loss with respect to, or the derivative, or the gradient of the loss with respect to that weight. And then we have this backpropagation step, which calculates the loss at the previous layer by multiplying the loss at the next layer with respect to the weight that you're sort of going along to get to that layer, and doing this sort of extra gradient step based on whatever the activation function is. So our basic algorithm is going to be, forward propagate the network, calculate some loss, and then what we want to do is calculate the partial derivatives of these weights with respect to the loss, and backpropagation is just an easy way of calculating those partial derivatives by doing sort of this multiplication along these same weight vectors that we had before when we were doing forward propagation. So we can think of this all in terms of just doing matrix operations, which is cool because matrix operations are super fast. So the output, if we have sort of two layers, so imagine we have some layer of neurons x, and we have sort of the next layer of neurons y, we are going to calculate sort of the output here. And the output at some value h is going to be some weighted sum of the input. So we have our w's here, and we're going to multiply them by the input x. And so whi can be thought of as the weight that connects to the output neuron h from the input neuron I. So we're going to sum over all of our input neurons the value xi of those neurons by the weights hi. And we're going to add on some bias term because it's neural networks, we like biases. As we talked about before, it allows us to sort of shift around our predictions so that it doesn't necessarily have to go through the origin. And then we're going to apply phi, which is our activation function. So our output of layer y is just this weighted sum with phi applied to it. We can think of that in terms of matrices as we have this weight matrix w, and we're going to take some input x and multiply it by w, and we'll get some output matrix z, and then we can take this output z and add on our biases and take phi of sort of all of the elements of this sum independently, and we'll get our actual output y. And so we have these matrices that we're talking about now, which, matrices just, if you do matrix multiplication, you're just doing weighted sums, so this kind of makes sense. We can imagine sort of when x is a vector, then when we multiply x by w, we're going to get basically another vector, which is the result that we would imagine for a single example in layer y of doing these weighted sums with our weight matrices w. We can also imagine basically batch processing a bunch of examples at the same time. So x could be a vector of sort of the input for a single example at some layer. X could also be a matrix in itself. It could have multiple rows. And each of those rows are going to be multiplied by this weight matrix sort of independently. And the output that we get, z here, will also have a bunch of rows as its output. So instead of basically feeding examples into a neural network one at a time, we can also imagine feeding in a bunch of examples at the same time and sort of stacking them on top of each other in this x matrix. And then we can do just this big matrix multiplication of x, which may have a bunch of examples, by our weight matrix w, and we'll get some output z. So in particular, we can kind of think about the dimensions of these matrices. So our x matrix is going to have dimensions m rows by k columns, where k is the number of input neurons in our layer x. And m here is going to be the number of examples that we're looking at. So if we just want to process a single example, m will be 1. But we can also make m be larger than that. M can be sort of any size we want because it's just a matrix. And then our weight matrices are going to have dimensions k by n, because for every input value in our layer x and for every value in our layer y, we're going to have some weight that connects those two neurons. So we need basically the squared number of neurons of k and n, and our weight matrix w has basically that many weights in it. It has enough weights to connect every neuron in layer x with every neuron in layer y. And then when we do this matrix multiplication of an m by k matrix with a k by n matrix, the output is going to be an m by n matrix. So we have our output matrix z is going to have dimension m, which is the number of rows or the number of input vectors that we sort of put into this layer. And it's going to have n columns, which is the number of neurons that we have in layer y. So that's good. The forward propagation math sort of works out. Do people kind of understand at least a little bit? It takes a little while to wrap your head around like matrix multiplications and why this makes sense. But I sort of think of it as just like, you look at the dimensions of the matrix and they kind of work out for doing the processing that you want. Do people sort of understand why doing these matrix operations would correspond to running an input through a single layer of a neural network? People have any questions about these matrix operations? Cool. So what are we doing with backward propagation? We want to take the error that we have at some layer y and backpropagate it through these weights to form some error that we might have at layer x. And so if we're thinking about doing this in terms of just weighted sums again, if we think about the error at some node I, we're going to have to look at all of the weights that come from layer x, from all of these nodes, into layer I, or sort of all of the weights that go out from layer I to this next layer, layer y. And we're going to have to think of all of the deltas that we have at layer y, all of the sort of loss information that we have at layer y, and backpropagate them through these weights to form the loss that we have sort of di in layer x. So di in layer x is going to again be a weighted sum, but this time we're going to be, OK, this is a little weird because this should be h, I think, instead of, I switched from using j's because, so this is a j, but it looks like an I, which was very confusing, so I switched to using h's. But this is going to be a sum of the delta information in layer y multiplied by the weights that connect node I to layer y. And we're also going to do this extra gradient computation based on what our activation function is. So remember that when we're calculating basically our partial derivative at this layer with respect to our loss, we have to factor in the gradient information that comes based on our activation function. And so if we think about basically doing this backpropagation, we can again think about it in terms of these matrix operations where we have some loss information associated at layer y, and we want to calculate the loss information at layer x. So what we're going to do is, again, just a matrix operation of the loss information at layer y with our weights. In this case, we're going to have to transpose our weights because we're going the other direction. So instead of going forward through this network, we're going to basically go backward. We're going to run the neural network backward to calculate our new partial derivative information. And we're going to have to do basically this multiplication by the gradient information at each of these nodes of our activation function as well. So we can think of basically the partial derivative information at layer x as being this multiplication of our weights by our partial derivative information at layer y by our gradient information of our activation function for whatever the input was at some neuron. Do people sort of see the correspondence with the matrix operations that we're talking about here with the sort of intuitive or mathy definitions that we gave for backpropagation earlier? Because in practice, basically, this is the right way to implement backpropagation. You don't want to have to fool around with like actually forming these connections and like figuring out which connection goes to which other node. You want to do these things just as these big matrix operations. It makes life a lot easier. So we started out with the intuitive explanation of backpropagation. We went to the math behind it, and now we're talking about how we do all of these operations in terms of these matrix operations. And the last piece of information that we might want to think about is basically how do we calculate the weight updates for all of these weights. The weight updates are basically going to be just the partial derivative information that we have at layer y multiplied by the input that we had from layer x. So if we want to calculate basically how are we going to update the weight whi, we're going to take all of the, oh, lost it. What happened? Oh, I think I ran out of battery. All right, so we want to figure out basically the weight updates for some weight that connects basically layers x and y. We're going to think about the loss that comes from layer y and the input to that weight at layer x, and just multiply those two things together. And again, we can think of this as basically this matrix operation where we have our inputs from our layer x, and we have our gradient information, delta y. And basically, these are going to be two vectors. And if we multiply those vectors by each other, sort of the end result, we're not doing basically the dot product. We're doing this matrix operation where one of them has the size of the input of x, and the other one has the size, sort of the number of outputs in y. And so the matrix operation, we end up with this matrix that is sort of the number of units in x by the number of units in y, which corresponds to all of the weights that we have in w. And so we can sort of frame our weight updates as well as this matrix operation. Should be coming back online. Cool. And so this is what I just talked about. We have, there we go. We have our, we want to calculate basically the change that we're making to w, and we have our input x, and we have this gradient information at y, and we can just basically take x, which was a vector, and take the transpose and make it into a column vector instead. And when we do basically this matrix operation, we end up with this matrix that is the same size as our weights that we had before, but this will basically be a calculation of the input x multiplied by sort of the derivative information that's coming from y. And each entry in here will correspond to the amount that we want to update the weight w. Basically, the partial derivative at w of our loss function for the entire network. And so again, we can do this in some sort of batch processing mode. So x may have basically a bunch of rows in it. So x transpose will have a bunch of columns. And correspondingly, our partial derivative information will have a bunch of rows to it as well. And we will basically get that the weight update for any given weight will be the sum of all of the inputs for the different examples at this particular node I with the gradient information at that particular node h. But we'll do that sort of at each of these weights independently. We have a question. Yeah, so I mean, these are just two matrices, right? So you have w and delta w, and you can imagine that you might be using a matrix library. You can just subtract matrices element-wise from each other. We talked about basically you have this learning rate thing, so you don't necessarily want to just subtract out the actual partial derivatives of w. You may want to scale them by some amount first. But it ends up being just pretty simple matrix operations where you'll scale that entire matrix by some scalar and then either subtract it or add it from your weights w. Any other questions about basically doing these weight updates but in matrix form? Because this is going to be your homework. Cool. So now let's, yeah. We're doing C still. But it's just matrix operations. I wrote you guys a matrix library. You'll be fine. It's super easy. You don't use NumPy? NumPy is garbage. So let's talk about basically things that we have to think about with neural networks. So we have our model, and we talked about basically we have a couple sources of error when we think about our model. One potential when we're fitting a model to data is that we sort of underfit our model to the data. And this happens basically, if you happen to choose like a linear model for some data when a linear model isn't really appropriate, you'll have a bunch of error because the bias of your model is too high. The corresponding sort of thing happens when you pick a too powerful model, where instead of underfitting, we get overfitting, where if we have a super powerful model, it's going to sort of precisely fit to all of the noise in the data, and then you're not going to generalize well to new examples. So way on the right over here, we basically have a really overfit model where you can imagine that basically it thinks that all of the points in this region are going to be red, when in fact it's pretty obvious that like this is just sort of a weird outlier, and actually most of the points that fall in this region are going to be blue. And so in the future, when you're predicting new data points that are coming in, you're going to make a bunch of errors in sort of this region, and this region, and this region. because you have this model that overfit to your data and doesn't actually fit the underlying distribution very well. So what we really want is some sort of happy medium between these two things. We want to sort of balance off this trade-off that we're doing between our bias and our variance and get some model that sort of models the data well but kind of ignores the noise or doesn't think about the noise too much. So how do we do that? There are a few options for doing this, and we've talked about some of them before. One option is just pick the right model. And if you have sort of a distribution that looks like this, you may want some quadratic function that separates out the two classes, but you may not want some sort of higher order polynomial that's going to do some crazy things to your data. But it's really hard to kind of know beforehand what the right model is for a given set of data. It's pretty easy if you look at sort of two-dimensional data that looks like this, and you might think that like, oh, let's just visualize the data and we can kind of pick the model based on that. But in practice, most of the data that we're talking about is like not just high dimensional, it's like really high dimensional. And when you start thinking about high dimensional data, basically a lot of the intuition that you might have kind of goes out the window. And so especially like if you think about images, if you have a 256 by 256 image, or 256 by 256 by 3 channel image, it's like 100,000 pixels or something, and each of those pixels can vary by some real number. You have this super high dimensional data, and it's like totally unclear, no matter like how you visualize the data, how you would go about picking sort of the correct model. So another thing that we talked about before is we have ways of basically taking a weak model and making it more powerful. And if we do this, we can sort of take this weak model and over time kind of crank it up and make it sort of a little bit more powerful using boosting by sort of adding on more and more models to this ensemble. And eventually we'll kind of take a model that looks like this and increase its power more and more, and we'll hopefully get to something that looks like this. And then if you sort of kept adding on more and more potential models to it, you may eventually end up with some more powerful model that starts overfitting the data. And hopefully, sort of given your training and validation data sets, you can kind of pick the right number of models to use in your boosting, or you may come up with some other ways of basically avoiding going too far with your boosting. So that's a way to take basically a weak model and make it more powerful. There are also basically ways of taking strong models and making them less likely to overfit or making them less powerful. And this is called regularization. So we have this neural network, and we talked about with the universal approximation theorem, it's this really powerful model. And when we start fitting this really powerful model to our actual data, we're going to start overfitting very quickly. So we're going to have to start thinking of basically regularization strategies of dealing with this. And we thought about before, basically with SVMs, we wanted to kind of pick basically the best linear classifier. And the way that we did that was we picked a linear classifier based on some constraints that minimized the values of the weights W. So we wanted this linear classifier that still basically perfectly separated the two classes by some margin, but we wanted to minimize the weights such that the two classes were still separated by that margin. With neural networks, what we're going to do is kind of a similar thing, where we're going to focus on basically having these small weights W, but we're forming it in terms of sort of this optimization problem that we can solve with gradient descent. So before, basically, we were solving for the weights W that minimized this loss function over our data L. Now, basically, we're going to add in this extra term, which is just some measure of magnitude of our weights themselves. And so you can think of a bunch of different norms that you could use for this. If you've taken machine learning, you've probably seen like L1 normalization, which is lasso, and L2 normalization, and et cetera, all of the different normalizations that you can think about, where they each sort of correspond to different things. In practice, most people use in neural networks, most people use L2 normalization because we don't necessarily want to enforce sparsity, which L1 normalization would do. So we're basically, to normalize this neural network, or sort of avoid overfitting, what we're going to do is basically still try to learn a model that minimizes this loss function, but we're going to try to learn a model where all of the weights are sort of small. And I don't have a great intuitive explanation for why this makes sense, except for what we were talking about earlier with SVMs, where basically you can think about an SVM can basically arbitrarily increase the size of some margin by basically cranking up these weights to be higher and higher. You can think about basically neural networks sometimes do the same thing, where they might find some weird combination of features that works really well for some given data set. And if they sort of happen upon this, they might start cranking up some weights to be really, really large. And in general, really large weights, or sort of weights weights in neural networks where some of them are much larger than others, we tend to think of as probably overfitting to the data in some kind of way. So what we want to do is basically minimize this joint loss function where we have both the loss of our model and also the L2 norm of these weights. And we're going to use this parameter lambda as sort of a scaling factor between how much we care about minimizing the loss and how much we care about minimizing the L2 norm of the data. So now if we think about basically what this means for our weight update function, we have this lambda, which is our regularization parameter. And if we have a higher lambda, we basically have more penalty on these larger weights. We have a less powerful model. If we think about a lower lambda, we have basically less penalty and probably more overfitting. And when we think about our gradient descent update rule, we're basically still taking the partial derivative with respect to each of the weights of the loss function. And now we have this added term of lambda. Oh, sorry. So this is after I've already done sort of the gradient computation. So if you think of what the gradient of the L2 norm of W is, it's just going to be W. You have sort of the sum of each of the weights squared. And when you think about taking the gradient of that with respect to one of the particular weights, you're going to get 2 times that weight. And in practice, we often sort of think about, but often don't write, 1/2 of the L2 norm. So the partial derivative with respect to the L2 norm, or the partial derivative with respect to some weight of the L2 norm is just going to be that weight itself multiplied by this scaling factor lambda. And then when we distribute out sort of our learning rate eta, we're going to have this new weight update rule where we take the weights at time t plus 1 are going to be the weights at time t minus the gradient step that we were doing before, and then minus some scaled amount of the current weight that we already have. So at every time step, we're basically just going to subtract out a little bit of the weight as part of our weight update rule. So hopefully you can kind of see you don't want lambda to be really large because we'll immediately just sort of set all of the weights to 0, and that would be bad. You would get a model that doesn't really do anything. So this is kind of a method of regularizing neural networks, sort of the most common one called weight decay. We can also think of basically, we often have some other random issues that crop up when we actually start training these neural networks. In particular, sometimes training them can be really slow. So we're doing stochastic gradient descent, and we're making a lot of these really little updates. So we have this learning rate eta, and eta is going to be really small. And so we're going to look at a data point, figure out the partial derivatives, and then move by just some really small amount, and then basically do the entire process again. And so imagine that you're on some lost surface that looks like this. And we're here, and we're going to make this little gradient update. And it's in this direction, so we've gone here. And then it's in this direction, so we've gone here. And maybe our eta is set pretty small because we don't want sort of our derivative information to go crazy or our updates to kind of go too far. So we might end up in a situation where over and over again, we're kind of making some update in the same direction multiple times. And what we would like to do is basically, as long as we're going in the same direction with our weights, as long as sort of the changes that we're making to our weights are the same after multiple iterations, we basically want to speed up how fast we're going in that direction. So instead of basically making these really small shifts over and over again, after a couple of them, let's start making larger and larger jumps in that direction until maybe we start going backward in the other direction. And so for stochastic gradient descent, we're going to add in this new term called momentum. And what momentum is going to do is basically, as long as we're moving in the same direction, we should start going further and further every round. And so before, we had this weight update rule where the changes that we were going to make to W are just our partial derivative of our loss with respect to that weight. And now what we're going to do is basically the changes that we're going to make at time t of some W are going to be the partial derivative with respect to the weight of the loss function. And then we're going to add in some scaled amount of the updates that we made last round as well. So m is going to be our term for momentum here. And m, you can imagine, is basically being somewhere from 0 to 1. So if our momentum is set at 0, we just have our normal gradient update rule. And you don't want to set m to be 1 because really bad things can happen. But in general, you might set m to like somewhere between 0.5 or 0.9. And what this is going to do is basically, every time you update a weight, you're also going to add in a little bit of the update to the weight that you made at the time step before that. And then when we actually think about what the weight at time t plus 1 is going to be, it's going to be the weight at time t plus our learning rate multiplied by our weight update that we calculated here. So we've just added in basically a little bit more of the weight update that we made at the time previous. A cool side effect about this, so this will have the effect of basically speeding up gradient descent if we keep moving in the same direction. What this also does is sort of smooth out updates if we have gradients in a bunch of different directions. So you can imagine that with stochastic gradient descent especially, if you have a small batch size, you're looking at basically the partial derivative of that weight for a single input or sort of a single training example. And you're going to have really noisy gradients. But what this momentum term does is almost some sort of a rolling average, or sort of this moving average to the updates that you're making to W. So you're going to smooth out basically all of these weight updates a little bit, and it's not going to have quite as much noise as you were having before, because your update that you're making to the weights also has this extra factor, which reflects all of basically the updates to the weight that you've made in the past. So it sort of smooths it out a little bit, and it has a bunch of nice properties when we're doing gradient descent. So now we have our neural network, and we want to update the weights, but we also want to add in this term for weight decay and this term for momentum. So at every time step, we're going to basically calculate how much we're going to change that weight. And how much we're going to change that weight is basically the gradient of the loss with respect to that weight minus some amount of weight decay plus some amount that depends on basically your term for momentum, which is based on the amount that you updated the weight basically the last round. And then when we actually do the weight update for the weight at time t plus 1, we are going to just take the weight at time t and add on some scaled amount of this weight direction, or sort of this gradient that we determined for the weight. And this scaled amount is based on the learning rate, eta. Finally, we can think about, we talked about these activation functions, phi. There are a bunch of different options that we have for them. And we have this universal approximation theory that holds when they're bounded. But we can have some problems when we use bounded activation functions. So just very quickly going over what some possible options are. We talked about linear activation and why that's basically a bad idea for most of the hidden layers. Logistic activation we've seen before. And this is an activation that people will also use in sort of the hidden layers of a network because it has these properties where it's bounded and it's monotonically increasing. Tan-H is just a scaled and shifted version of the logistic activation function. The problem with these two activations is, remember that when we're doing this gradient backpropagation, we take into account the gradient with respect to the activation function when we're backpropagating our deltas. And the gradients of these two functions, especially when we're out here in the domain, sort of at the very negative or very positive parts of the domain, we have here the gradient of the activation function, and basically it's going to shrink down to be really small. It's going to be basically 0 as we start getting out too far in the positive or negative direction for both logistic and tanh. And what that means is basically if your output is really large and the output of your logistic function is 1, you're going to have very little gradient information to use when you're doing your weight updates. So you can sort of stall out in your training. And so people are sort of starting to use less saturating activation functions. So we have a couple examples here of rectified linear units, where it's going to be linear when the domain is positive, and we're just going to set the activation to be 0 if the domain is negative. This has the same sort of saturation problem, just sort of on half of the domain, where if the input x is negative, then our gradient is going to be 0. So people also use this sort of leaky version of ReLUs, where we're going to have f of x equals x if x is positive, and f of x equals 0.1 of x if x is negative. And that sort of preserves some gradient information no matter where you are in this domain. So that's cool. We have a ton of hyperparameters now. It's really hard to know which ones to use. That's where you rely on some hyperparameter dark magic. So these are the one true correct values to use for all of these hyperparameters. They've sort of been given to us from on high, and we can just sort of plug them in. And